powerful about what we're doing. And it still might get lost, and that's okay. I'm going to do my best. I want this to be a cerebral conversation. And I was asked earlier what cerebral means. Thoughtful. And somebody then said, well, why don't you say thoughtful? Because I think the word cerebral sounds cooler. Who agrees? Cerebral sounds cooler than thoughtful. Yeah, I think so too. So when you know you have a choice of using thoughtful or cerebral, I like using cerebral. It somehow feels like it's more than just thoughtful. Like it's thoughtful with a purpose. So the point of yesterday, aside from all the mathematics I was involved in getting there, was to... And one less kid goes to prom, I'll probably be okay. We reached the break-even point today, so whatever, I don't care who goes to prom now, we've got enough money to pay for it, so yeah. I mean, I was never on the hook for the money myself, but prom's expensive. You see it $100, but I see the $38,000 it costs to put on prom. And I'm like, wow, that's a lot of money for dancing and all that. So, okay. Refocus, Mr. Shelton. Ready? We started here. Used Newton's laws and created a second-order differential equation. And I have to say this just right or it doesn't work, so bear with me. We then went through a very convoluted procedure to create a whole wide array of relationships related to the spring and the mass that culminated in this influential term which determines how that system works. Everybody okay with that? You understand what I mean by all of that? So if you know this is how the external force on your system is, that K becomes super important. It determines everything. It controls how the system behaves. And you can make predictions. We know what the displacement, velocity, acceleration will be. We got equations for that now. We know what the period of oscillation is going to be, how much energy is going to be how fast it's going to be going, we know everything. All because we started knowing that it was this kind of force. And yesterday, we got there. If you buy into the idea that theta equals sine theta, then we're able to buy into the idea that this, oh, Mr. Shelton, I should just quit and empty trash cans for a living, be more successful. Then we bought into the idea that we can substitute this distance for this distance. Right? That was the whole goal. I know it sounds ridiculous, but that was so that we could eventually write that the net force equaled minus mg over L times S, and that equaled ma. That was our goal. Now, I wanted to satisfy that goal because although we did all the beginning work with an abstraction, a mass on a spring that I could never set up in the classroom because I don't have a frictionless surface and a perfect system in which there's no air resistance and an ideal spring. I didn't have those things. But I still created my model based on that. And from that model, I used what we knew about Newton's laws first semester. Net force equals ma, draw a free body diagram, break that diagram up into x and y. Remember all those rules? And we derived this, which has a k in it. That's k. That's the constant times displacement. And because of that, K over M is now mg over L over M. I'm replacing K with that. Now, this simplifies, right? The masses cancel out. So I cancel out the masses and I get the square root of G over L. So what does this mean? Well, quite frankly, it means in all of those equations where there's an omega, Omega is now the square root of G over L. So if I have period equals 2 pi divided by omega, then I have period equals 2 pi times the square root of L over G. If I have V equals x naught omega times the sine of omega t, well, then I know minus S naught square root of G over L times the sine of the square root of G over L times t. You tell me t, I will tell you how fast the thing must be going at that instant, because this is v as a function of t. I can plug that omega in anywhere, and it should perfectly predict the nature of the system. Let's try it. Let's see. Remember, this was derived without ever building a pendulum. Would you agree with that statement? Did we ever build one and test it ahead of time, or try a bunch of experiments to see if it would work? We're going to do it right here. We're going to see if... Oops. What's that? 67 centimeters is from the top to where the mass is inside BB-8. I hate it when my watch tells me to stand. I have not sat down since 8:30 this morning. You guys done? You have a time? 1.64 seconds? Everybody agree 1.64 seconds? That's good, because that's what I was hoping you would get. You know, mostly because I used the same BB-8 as last class period. So 1.64 seconds.